Hi everybody, my name is Patricia Garza. I'm going to talk about the cold plug press process for my class Quality Assurance. For this to happen, I want to explain where am I working. I'm the industrial engineer for the assembly line process of the drive units. The drive units are the combination of the engine and the transmission for the electric vehicles that we are now launching. This is still a process that we are launching, so that's why we want to optimize the whole process. So let's start talking about what is driving this project. As you can see in the diagram, we have the case line that starts the main line. And the main line has all the process, and at the end moves the drive unit for the testing process. In this process, or the cold stand, as we know, it checks different parameters, but one of the most important parameter is the noise. In this process, we have to review if there is anything wrong with the case line and the cold plug process that we made, and if it's okay, then there is a final drive unit ready to be shipped to the assembly plant ensemble. But our current restriction is the case line, as we can see here, because there has the lowest capacity compared to any other process that we have on the plant. This is why we want to review this restriction on the what is the bottleneck happening in here. So in our process, the cold plug press process is reflected as the bottleneck of the case line. This is due to different causes, which one of them is the high level of rejects. These rejects are for high force, or target or upper limit as the 6 kilonewtons. And we will see on the control chart that we are going to show you that the mean is 5.9, which is already almost on that limit of the 6 kilonewtons. We can see on the individual chart of the force that there are different points out of the specification, out of control, which is why we need to do a better deep in this data. When we have those points on red, we are making downtime because there is a constant maintenance intervention to review the station. Also, if there need to be an alignment for the robots. This is causing more loss on our productivity. And what we have to review also is the process capability. As we saw, there are different points that make our process out of control. And also we have the chart for the cumulative sum where we can see that there is only going up. There is no control on this process, and if we do not do something, we will have a worse process. And we can see it here in the process capability report for force, where the most of the process data that we already have, it's under over the limit. The 28% right now is above the limit, the upper limit. And this graph tell us about how is it going to be behaving with the pass of the time. And we can see at the bottom of the right side that the exponential overall performance is showing that 28% will increase to 38%. And the other thing that we can see is the PPK it's 0.1, which indicates that we have no control of the process, because as we can know, a PPK high, it's a high high level of the control process. One of the things and tools that I learned in this class is maybe to implement a different design of the experiments. There are different types, but one of the better to use in this case is a the Taguchi method. The Taguchi method asks for first for the control factors. The control factors that we are going to use for the design of the experiment are four. First of all is the press force that we are injecting on the cup lock. The second one is the cup lock material, just to know if we have to make it a little bit harder. And the other two are for the press tool, because one of them because the process can be changed, and this um, will be for the diameter or the material of the press tool. We are currently having a tool change every 2 weeks because it damaged. Maybe we need to review the process if it's the correct material of the press tool. And the other tool for this project is the acceptance sampling technique that we need to review. I'm showing you the operating characteristic curve just to know if the sample size is okay, and also the acceptance number. Currently, we have a 30 sample size of 30, and the current number is 1, but I wanted to review how it will be behaving if we change those numbers. The best behavior is when we have the 70 as the sample size and 1 as the acceptance number. But this is a little bit hard because the time we need to review the 70 with a 70 sample, it's longer than we expected, and we cannot be running at the same time at to complete the measurements. So that's why we are taking the 50 sample size and also the acceptance number of 1. The the best behaviors are represented in that little chart, where we can see the 50 on the 50 sample size of 50 and the acceptance number of 1 has the lowest AOQL and the percentage effective of 3. So just to end up with the next steps, there are two. First, the redesign of the pressing tool, just to review if it's from the material or also the diameter. And we are reviewing the acceptance sampling as continuous improvement. That will be it. Thank you so much for your time. See you later.